Hello, and welcome to this Real Python video series on basic data types. In this course, you'll be looking at integers, floating point numbers, complex numbers, strings, Booleans, and some built-in functions which will help you work with all of these data types. Let's get started looking at integers. Integers. What is an integer? Well, an integer is a whole number, the kind you started out counting at when you first learned about numbers at school. And in Python 3, an integer is any length up to the memory limit of the computer, so you probably won't run out of integers that you can use. The default is in decimal, base 10, but as you'll see, you'll be able to define them and view them in different bases. And you're going to see how to create integers and different ways you can work with them in the following videos. Throughout these workshops, the coding will be done using BPython, which is a version of the Python REPL that uses docstrings and color coding to make understanding code more simple. With that housekeeping out of the way, let's look at ints. As you've already seen, an int is a whole number, and it can be created easily, as seen here, creating a variable a with a value of 1 and b with a value of 10. And we can see that a has a value of 1 and b has a value of 10. It's possible to do simple arithmetic, such as a plus b, seen here, or a minus b, and the results are as we would expect. As mentioned previously, the default for these numbers is decimal, or base 10, but it's possible to use other bases. So we can have them in binary, hexadecimal, or octal. So if we want to define one in binary, here we can see we're defining C, and we start off with 0b, and then put in the binary digits that make the number up. And now we've defined C, and if we hit C and enter, the value, as you can see, is 343 in decimal. This is a nice, quick, easy way to convert binary numbers to decimal. Here, one can be defined in octal, again using a similar pattern, but 0 and then O for octal, and inputting some octal digits. And again, D equates to 153,802 in decimal, and E will be defined in hexadecimal using 0x before the digits which make it up, in this case AC4D, and that equates to 44,109 in decimal. Now sometimes you'll be in a situation where you've got a string which is a number, but you need to equate it to an int. So here I'm going to define mynum as a string of 1, 2, 3, 5, and if you try and do some addition with that, mynum plus b, you can see it doesn't work. We get a type error, and you can see that it's trying to concatenate the string and b. So it's actually not doing what you'd think at all. It's certainly not the addition we were looking for. So what's needed is to convert mynum into an integer to allow maths to be performed on it. So that's done using the keyword int, and inside we'll put the original variable mynum, and you can see that now equates to the number 1235, whereas mynum is the string with the quotes enclosing it. And there you can see the int doesn't have any quotes. Now we can define mynum2 as the int of the value of mynum, and now it's possible to do the maths on it. Plus b gives us the value of 1245. As you'll see with all of the variables in this course, it's possible to inspect the type of them using type. So here type, and then we put any of our variables in, and we can see that they are the class of int, which is for integer variables. And hopefully you can see that the reported class of int is the same as the keyword used to cast a variable into that type. You've already seen how to define an integer using a base of binary, oct, or hexadecimal, but it's also possible to perform the translation the other way round. So now you're going to see that in action using the mynum2 variable and converting it to different bases. So first, it's possible to create a binary representation of it using the bin keyword. And there you have the binary representation of mynum2. Using oct gives us the octal representation of mynum2. And using hex gives us the hexadecimal version of that number. Remember, it's still the same number, we're just representing it in different bases. And you can see that these are three easy ways to represent the same number in binary, octal, or hexadecimal. And that covers integers. floating point numbers. Now, what is a floating point number? Well, a floating point number is any number with a decimal point, and these are represented differently in Python's memory than the integers we've already seen. And while you've seen some maths in the previous section, any division operation will return a float, as you will see in a little more detail later on. And they can be defined using scientific notation, such as seen on screen here, with 4 times 10 to the power of 3, which is equal to 4,000. But there are some limitations to floating point numbers, as you will see at the end of this section, and this is something you will fall foul of at some point and need to be aware of. The simplest way to define a floating point number in Python is to create a variable with a decimal point and a number after it, such as seen here, where we have a is equal to 4.2. You can see that the value is 4.2, and entering type A shows a class of float, and a floating point number has been created. Now, a number which has got a decimal after the point, even if it's 0, will still be a float, so while that could be represented as an int, it is a float. And coming up, you'll see that the result of division will always be a float. So, going to define some variables to work with to make the division clear to see. So we'll have C as 10, and then D is equal to 4. So both of those are ints, but if we make E equal to C divided by D, we can see the result, which is E, which is a float. Now the result of division will always be a float, even if the answer could be an int. So obviously in that case, 10 divided by 4 is 2.5, so the answer would need to be a floating point number. But if D is redefined to be 5, and make F equal to C divided by D again, we can see that F is a float, even though the answer could be an int. Python does have the integer division operator, which is the double divide sign as seen here, and we can see the result is 2. But there is another thing to be aware of with this. It will always give you an integer result, which may not be the exact answer you're looking for. So here, if we take C and divide it by 4, the answer should be 2.5, but we can see it's also 2. So this is something you need to be aware of when choosing which division operator you're going to make use of. Sometimes floor division gives you the right number, and other times floor division gives you the wrong number. Now, it's possible to take any number, including an int, and turn it into a float using the float keyword. So this can be seen here by making I is equal to float of 3, and then if we look at I, we can see I has the value 3.0. Now, something else which is useful is being able to define numbers using scientific notation. Now, if you're not aware of what scientific notation is, a little bit of research on Wikipedia will help you understand it, but the general form is there will be a number at the beginning, and then the second part will be the powers of 10 which are being applied to that number. So here we're going to define the number j as 4, and then use an e to denote scientific notation and a 3, and you can see that equals 4,000 because we have a 4 at the beginning, and then we have 3 powers of 10, which is multiplied by, so it's 4 times 1,000. The powers can also be negative, as seen here, so 4e to the minus 3 equates to 0.004, because 10 to the minus 3 is 1,000th, and then we have 4 of those, which is why we have that 4 there. Sometimes the negative form is a little less intuitive, but with a bit of practice, it will make sense. Now, floating point errors were mentioned at the beginning of this section, and this isn't something that only affects Python, but all computer languages. So here's an example of floating point arithmetic not working in the way you would think. And it's pretty easy to encounter these kind of errors. So let's just define some simple variables. So here you can see a is equal to 0.2, and b is equal to 0.1, and c is going to be a plus b. Now, I'm sure you're all aware of what the answer should be, of 0.3, but if we look at c, we can see there's a tiny error at the end. Now, this is something that you will need to be aware of, and you'll need to take it into account when programming. Now, that's obviously something that's outside the scope of this introduction video, but it is something you'll need to be aware of. And the first time you encounter it in the wild, you'll probably scratch your head for a while, but after a while, you'll know what it is and know what to look for. Complex numbers. A complex number is expressed in the form of ax plus bj. It has two elements, the real element and the imaginary part, where j is the square root of -1. And if your maths has gone to a certain level, you probably have come across complex and imaginary numbers. They're useful in a number of fields, and Python is perfectly happy dealing with them. creating complex numbers is easily done, as you can see here, in the form a equals 2 plus 3j gives us a, and if we look at the type of a, you can see it's of the class complex. And in this class, it's possible to do mathematical operations such as addition. So let's define another number, b equals 3 plus 5j, and adding a plus b gives us what we'd expect, 5 plus 8j. You can multiply them, such as a times a gives us minus 5 plus 12j. And complex numbers in Python are capable of doing any of the sort of arithmetic as you'd expect to be able to do with them in mathematical work. So if you're doing anything that involves complex numbers, you'll be able to use this data type to allow you to do it simply and easily. Strings. So, what is a string? A string is a sequence of 0 or more characters. Strings can be enclosed in double quote or single quote characters, and if you need to include either of those in a string, it's possible to do that. And strings can also take the format of raw or triple quoted strings, both of which you're going to see later in this section. Defining a string is straightforward. As you can see here, defining the string hello world enclosed in double quotes, but it can also be enclosed in single quotes. And as you can see, both have the same representation when printed by Python. Choosing which to enclose the string in can be important because sometimes you'll want to have one or the other inside a string. So here you can see a string is being defined using double quotes, and it has a single quote inside it, which Python is untroubled by. It's happy to print that out. But if that was done using single quotes throughout, BPython is already giving us a coloured hint that this isn't right, and we have a syntax error because we have the beginning of the string which is defined up to I wasn't, and then the rest of the line doesn't make sense to Python. So that is not the way that you do that. Now, clearly, you can do it the other way round. So you could have a single quoted string which has double quotes inside, and that will work perfectly well. But trying to do that using double quotes throughout won't work in the same way we've already seen. And you can see that BPython is color coding our problem to highlight it to us. Python has got confused about this. We know that that should be the whole string all the way there, but that's not the way that Python sees this. Sometimes there'll be examples when you need to use single and double quotes inside a string, and you're going to see how to do that a little bit later. As you would expect from the other videos you've already seen, if we use type on one of the strings we've defined, we can see it's of the str string class, and this can be used to convert other data types into strings. So if we want to turn the number 51 into a string, we can just define it using g equals str51, and now g is the string 51 rather than the int. Strings, escape sequences. As you saw earlier on, it's possible to need single or double quotes inside a string, and if you need to have both inside a string, it's not simple to see how to do this. So here's an example where we have both double and single quotes inside a string. So where we're quoting something with an apostrophe inside it. Because inside this string we have both double and single quotes, neither enclosing quote type is going to work. So trying to redefine it using single quotes won't work either, although it will break down in a different place as highlighted by BPython in colour. So as you can see, it doesn't work because here we've got that single quote as well as the double quotes inside. So initially this may seem to be an insurmountable problem, but fortunately a technique called escaping allows the normal interpretation of the character to be suspended and the string to be defined as normal. This is done by putting the / character before either the single or double quotes within our string, allowing them to be stored safely inside the string without taking up their normal role. Here, the desired sentence is being defined using single quotes, and then when the apostrophe comes along, a / is placed before the apostrophe, stopping it being interpreted as the end of the string. Now you can see that Python is happy with the definition of the variable because of the / used before the apostrophe. And looking at C, you can see how it's been stored internally. To see it the way it would be printed out for the user, we can use print, but you can see it's slightly different in the Python REPL, as highlighted here. So it's enclosed in those single quotes, and also it doesn't interpret the \t, whereas when it's printed out, that \t is reinterpreted as the single quote that we wanted. Using this technique, it is of course possible to have enclosed the string in double quotes and to have escaped these quotes inside, or even escape all of the quotes inside the text. Now, there is another use of escape characters, which is for special meanings such as new lines, and you're going to see that in action next. So here, D is being defined with the text, this is line 1, followed by \n, which together mean new line. This is then finished off with this is line 2, and the quotes are finished at the end. So here we have this \n character, which means new line. Now, when it's shown in the REPL, the \n isn't interpreted, but if we use print and print D, you can see that this is line 1 is on a separate line to this is line 2. Now, this is something you will use an awful lot if you're working with text files, and often you'll find you need to insert or remove new line characters from text. It's also possible to do it with tabs, with \t. So here you can see a variable is defined with some tab characters inserted in. And once again, printing this out shows that the tabs have been inserted between the words, so those tabs have now been interpreted. And in this case, each tab is equal to 8 characters, so you can see the spacing of the words is equal and isn't dependent on their length. It's important to be aware of the different escape characters you can insert into text, and the context in which they're used will change their effect. But on screen at the moment, you can see a selection of escape characters, such as \single quote and double quote, new line with N, carriage return with R, tab, which you've already seen, and the ability to define characters using octal or hexadecimal values. This isn't an exhaustive list of escape characters, but it's a good starting place. Strings. Raw strings. In a raw string, escape sequence characters, such as you saw in the last section, are not interpreted. So now you're going to see how to define a raw string and then how they are useful. Here a new variable A is defined with 2 pieces of text and a new line character in the middle. And you can see that when A is printed out, it has that new line character obeyed when it's printed. To create a raw string, the string is prefixed with an R, as seen here. Otherwise, the content is exactly the same. Printing this string out shows that the raw string means that the new line character is not interpreted by print and is left intact. This is useful in applications where the escape sequence characters are not to be interpreted normally, such as regular expressions, an area you may not be familiar with, but one's extremely useful in text processing. Regular expressions make use of the / character in a different way to normal text, and here raw strings come into their own by controlling the way that the string is interpreted. Regular expressions fall outside the scope of this course, but they're well worth looking into if you ever need to process text. Strings. Triple quoted strings. Triple quoted strings are most easily demonstrated within a program itself, so that's what you're going to see here. As you can see on screen, the triple quoted string has 3 quote characters at each end, and they can be single or double as long as they match each other. Printing this out just looks like a normal string, but triple quoted strings obviously have more to offer us just than extra typing. It's possible to put any kind of quote inside. As you can see here, the same quotes are being used inside the string as enclose it. As you can see printed out here, the double quotes work perfectly normally, but it's also possible to use single quotes with inside this triple quoted string as well. So you can see they offer an alternative to using escape characters, which you may find simpler to understand. However, their main use isn't to avoid the use of escape characters, but it's to allow strings which cover multiple lines, as you're going to see next on screen. And once that gets printed out, you can see it works exactly as you'd expect. Now, while this is a convenience, it probably isn't the most common use for triple quoted strings. Their most common use is providing docstrings for functions. So on screen first, a function is being created, as you can see. It's a simple function that just takes a value and prints it out. Now, while this is clearly a simple function and doesn't need much explanation, most functions you create will be more complicated than this, and when you come back to them, it may take you a while to understand what they are or what they do, particularly when they're named similarly. A good way to deal with this is to insert a docstring straight after the definition of the function. This will take the form of a triple quoted string, which provides a description of what the function does and what the parameters are that you feed to it. Now, while this may make sense while you're reading through the code, it's also useful while you're writing code. With most editors, when you use a function, it will pop up a hint which is made from the docstring that tells you about the function. As you can see here, takes a value and prints it to the screen, has been replicated. This may not be that much use in a simple program, but where you have a complicated one with multiple imports from multiple files, this can be really useful in telling you what the functions do. And notice that this is where the information that you see when using standard functions such as print also comes from. And any imported modules you've used in your programs will also have docstrings, which will help you understand how each function works. Booleans. What is a Boolean? A Boolean is a variable which can take two values. It's either true or false. In Python, false is equivalent to 0 and true is equivalent to any non-zero number. Understanding the true and false concept, particularly this truthiness, is key to writing Pythonic code which is more readable than it would be otherwise. You're going to see some examples of this later on in this section. As you'll see, defining a Boolean is as simple as setting it to true or false. Here A has been set to true, and you can see that the type is class bool. Of course, the other option is false, and B will be defined using that. In addition to this, though, objects are often evaluated as being true or false depending on their value. So here, setting the variable C to 1 means we can then evaluate it as a bool using the bool function. Here you can see that the bool of C is equated to true, and a bool of 0 equates to false. This is a key concept in Python, and we'll look at this in the next section. Booleans, truthiness. So here, D is going to be set to the value of 5, and let's see what happens when we check for equivalence. So we're going to see if D is actually equal to 5, using the double equals for equivalence rather than assignment with a single one. And we can see that that is true. So internally, Python evaluates these equations as Booleans. So if we check to see if D is equal to 4, you can see that is false. This is the foundation of the way that Python understands equations. Next, you're going to see a program which illustrates this a little more clearly. With the variable B being set to 0, it's then going to be checked as to whether it's true using the term if B. This is shorthand for if B is equal to true. Then B is true. In all the other cases, we will print that B is false. So at the moment, it's set to 0, so we would expect it to be false. And we can see B is false because B is set to 0. Changing B to 1 and running the program again shows that B is true. We can check this further with false, and you can see that B clearly is false as it holds the value false. And finally, setting it to true gives us a predictable result of B is true. But this concept extends further. An empty list is false because it doesn't have any content. This would also apply for an empty dictionary, as we'll see here with the curly brackets. But it's important to remember this isn't about the values contained in there. So if we have a list with a value of 0 in it, that is not false as it exists. Truthiness is a key component to writing Pythonic code, and once you understand it, your code will be clearer and simpler to understand when you come back to it, which is a key part of writing good code. Some editors, such as PyCharm, will inform you when you're not making Pythonic comparison statements and suggest improvements for your code. Built-in functions. So in this section on built-in functions, some functions for composite data types. You're going to take a look at some math, or maths if you're from the UK. You're going to look at type conversion functions. You're going to see some functions to do with iterables and iterators. Some functions for input and output. Functions for variables, references, and scope. And finally, some miscellaneous functions that don't easily fit into other categories. Composite data types. Composite data types are made up of other data types. So the first one we're going to look at is the list. And a list is defined using square brackets and a series of other values inside it, separated by commas. Once created, it can be printed out, as seen here. And elements of a list can be accessed using square bracket notation, which is 0 indexed, as seen here. So 0 will access the first element. So as you can see that 0 has accessed this first element, 1. Element 1 is the number 2, and so on. It's also possible to use negative indexing to access from the back of the list. So this will be -1, -2 will give us 4, and so on. And this is useful because you don't have to get the length of the list and then subtract away from that. That makes life much easier when dealing with lists. It's also possible to use slicing. So here we can go from number 1 to number 3. But as you can see, that's number 1, that's number 2, but it doesn't include the third element of the list. So much like many of the things we've seen already, the last of this is not included. So that's something that initially will probably catch you out a few times, but after you get used to it, it will make perfect sense and it can make some elements of coding much easier. Now lists are what's called mutable, which means it's possible to change them after they've been created. So we can change an element using the square bracket notation. As seen here, we can change element 1 by setting it to 6. And now if we look at the list, we can see that element 1 has changed from being 2 to being 6. And this allows us to work with lists in multiple different ways, and lists will be a core part of your Python programming throughout your career. The next data type we're going to look at is a tuple, which looks very similar to a list, but it's defined using normal curved brackets or braces. So as we can see here, we can access it in the way we've seen before with B0, B-1, and applying slices as seen before. But one thing we can't do with a tuple is reassign an element after it's been created. When we try to do that, we can see that the tuple does not support item assignment. Once you've created it, it can't be changed. It is immutable. Now that's a feature which can be useful, but it's also something that may trip you up from time to time. So that's tuples and lists. Next will be the set. Composite data types, set. A set is a data structure which can only contain unique elements. This will best be demonstrated in the context of a program. So firstly, we have a list which has multiple elements, and in this case, there are several examples of 3 in it. A set cannot do this, but it can be really useful for seeing the unique values within a list. So here, we're going to create a set B by passing it the list A when it's constructed. So all the values within A will be passed into B, and we're going to print out A and also print out B. And now you can see the program in action. And you can see that while the list contains multiple 3 values, our set contains only those unique values 1, 2, 3, and 4. So this is one application for a set where we can find the unique values within that list, and we can produce a list from that as well. So we can cast that to a list by C equals list based on B, and then we print C out. So now we have a list that we can access in the normal manner with only the unique values which are in that first list A. Now sets are the kind of thing you may have implemented yourself if you didn't know that a set existed, but as with all these examples, using the built-in Python function will be faster and less error-prone than coding your own version of it. Composite data types, dict. A dictionary is probably best thought of at this point as a lookup table, which allows you to store values in it, so you can store values with a key and value pairing. Now, if you're not sure what that is, this example should hopefully clear that up for you. So a dictionary can be created using the keyword dict, creating an empty dictionary, and then elements can be added to it using the following notation. We have a square bracket and the key inside that, and then we can set the value after the equal sign. So here we've set the value of name to be Darren, and we can put in other keys. So here, the value of age has been set to 48. And it's possible to print out the entire contents of the dictionary just by printing A. So here you're going to see the contents of the dictionary, and there's a few things to note. Firstly, the keys in this case are strings with a string age and name. They don't have to be, they could be ints or other values. And in this case, we've stored different types of data related to them. So name is a string, whereas the age is an int. Now, if you want to access the information stored in a dictionary, we can do this by printing A the square brackets, and then the key, in this case the string age, and that will work, and it returns the int 48, so it's looked it up in the dictionary and then printed that out. But what if we tried to access something that isn't there? So let's try accessing country and see what happens. And here you can see that a key error has happened because we've tried to access something with a key that doesn't exist. So this could cause a problem in your code. So a safer way to access values in a dictionary is using the get method, and here putting the key string in there, and it returns the value none. So the get method is a safer way of accessing values because it's trying to look up the value for country, and instead of generating a key error, it's returned the value none, which is a much safer value for your code to have to handle. So get is a much safer way of accessing than trying to access the values directly. And while your code would need to deal with that problem of returning none, it's much easier than having to deal with an exception. Dictionaries are an incredibly useful data structure and can help you with many situations across your programming career, and they're worth learning how to deal with efficiently and safely. And Real Python has a video series based on dictionaries, which will help reinforce your understanding and allow you to understand much better and use them efficiently. Math. First up is ABS, the absolute value of a number. So here, ABS will have the int 5 placed in there. And we can see it returns the absolute value. If we do ABS of -5, it also returns 5. So effectively, it removes the sign from the number that you pass in. Next up, the divmod function. And before we get to that, a quick recap of the modulo function, which gives you the remainder when a division is performed. It uses the percent sign and will give you one number back, which is the remainder from the division that you've asked for. In this example, we're going to take the number 15, then the modulo operator with the percent sign, and then 4, and the answer is 3, because that's the remainder when you divide 15 by 4. But there are situations when you want both the amount that the number divides into and the remainder as well, and that's where divmod comes in. We can enter two numbers, seen here, 15 and 4, and we get 3, because 4 goes into 15 3 times, and we get a remainder of 3. Another example will give us some different numbers to show which is which. So divmod of 10 and 3, we get 3 3s go into there, and we have 1 as our remainder. Next up, max. Max, as seen on screen, gives us the maximum of an iterable. So if we pass it a list of numbers, in this case 1 to 5, we'll get the maximum, which is 5. An important thing to remember here is this isn't maximum absolute value, but it's maximum value. So -4 and 2, the maximum number that it gives back, is -2, as -2 is greater than -4. Now, of course, we need the opposite function to that, and that is min, which will do a similar job, but give us the minimum from any iterable that we pass to it. So here again, passing that same list of numbers 1 to 5, we predictably get the output 1, and passing it -4 and 2, as we would expect, we get the answer -4. Next up, pow. Pow can take either 2 or 3 arguments. And with 2 arguments, it's equivalent to x to the power of y, but with a third argument, it performs a modulo operator on the result. Here we can see 3 to the power of 2 is 9, which is exactly the same as typing 3, double star for the power operator in 2. But pow can also take that third modulo argument, as we'll see here. And there you can see the remainder from that, when divided by 2, is 1. That's equivalent to what's seen on screen now. The next function is round. And as you would expect, rounds a number to the nearest integer. In this case, round of 4.5 is 4, and round of 4.6 is 5. Now this may appear similar to the int function you saw earlier on, but we can see that actually it's different. Int of 4.5 gives us the same answer, but int of 4.6 also gives us 4. The reason for this is int just ignores what happens after the decimal place and takes just the integer part, whereas round takes it into account. Next up, you can see sum, and sum sums up the iterable that you pass to it with an optional start value. So here it's being passed the numbers 1, 2, 3, 4, and 5, and it sums them to 15. But you can also add in an optional start value, which can be useful in some situations. So by performing the same calculation, but with a start value of 10, you can see that it comes to the sum of 25. This is the end of the maths section, and while none of these functions are particularly exciting, it's important to remember that they're there, as they'll save you time in having to code your own solutions, which could possibly have bugs in and would probably be slower than these equivalents. Type conversion. This section will cover converting between different types of data, the first of which is text and relies on the American Standard Code for Information Interchange, or ASCII for short. In recent years, Unicode has become more common as it represents many more characters and is the standard in Python 3. But if you need to use the ASCII function, you can pass it some text and it will tell you what can be represented in ASCII. In this case, the text can be represented in ASCII because all the characters are there, but if we pass it some Unicode text of a different character set, as you can see on screen here, it escapes them in a similar way as we've seen earlier and gives us character codes that represent those. This can be useful if you have a system which can only represent character codes that are in ASCII, but it's still possible to store these characters in an ASCII format that will then translate back to Unicode. The next one is CHR. And as we can see, that returns a Unicode string of one character. So the ordinal is put in this case 97 equates to a lowercase a, 98 equates to a lowercase b, and 65 equates to a capital A. Now you can look that up on a table for ASCII, such as the one which is on screen right now. So here you can see the 128 defined characters in the ASCII alphabet. So this table has been presented in groups of 8. And the reason for that is there's some repetition in this table which isn't immediately apparent if it's presented in columns of 10, etc. So for instance, capital A is 64 plus 1, which is 65, and lowercase a is 96 plus 1, which is 97. You can probably see how the two alphabets mirror each other's layouts, and how from 32 up to 63 there are numbers and punctuation characters, and from 0 to 31 there are a set of control characters which aren't commonly used anymore, but are implemented in some systems. Now, there isn't a table for the Unicode character set because it's much larger. It's got millions of characters in, so that would take many screens, but you can look them up online and print them out using the CHR function. They're often defined with hex entries. So in this case, we're going to enter a hex number of 0x and then 06A4. And we can see that equates to the character you see on the ASCII line. So CHR works for both ASCII and Unicode characters, as you would expect. CHR has a complementary function, ORD, where you can pass it a single character, such as the A that we'll see here, and it will tell you what the ASCII or Unicode point for that is, remembering that ASCII codes are the same as Unicode below 128. So here you can see capital A is 65, and if we use the character we've seen there, and paste that in, we can see we've got 1489. Another function you've already seen is type. Type can be fed any object, whether it's an explicit declaration or a variable, and it will tell you what type that is, such as string, or int, or float, or bool, or even a list, which we'll see later on in this series. So generally this is useful for when exploring variables and objects, but it's probably not something you should use typically in your code. There are a number of conversion functions that we've already seen earlier on in this series. We're just going to take a quick recap on those as they're so useful. So if you want to make something into an int, you can use int of, in this case, the string 1234 becomes the int 1234. And it can be done with different bases. So in this case, int 1234, where the base is equal to 16. So this is a hexadecimal 1234 equates to the decimal 4660. So this is useful for base conversion. If we do int 1010 and the base is equal to 2, we've put in the binary number 1010, which equates to 10, because we've got an 8 there and a 2 there. And those two add up to 10. Now we've also seen bin, oct, and hex. So if we do this, taking bin of 10, we get the binary representation of 10. If we do oct of 10, we get the octal representation of 10. So we've got 1, 8, and 2 units. And if we do the hex 10, we get 0x to show it's hexadecimal, and A is a single digit which represents 10 in hexadecimal. We can also convert to float using the float function. Here passing it an integer which becomes converted into a float. We can convert to complex. So in a complex number, if we pass it just a single int, we get 4 real numbers and 0 on the imaginary plane. But you can also define it in the normal way using 4 plus 3j in this case, and there you can see your complex number. We can convert other data types to strings if needed for printing, etc. So str of this int 1234 is the string 1234. So in Booleans, anything which isn't 0 will become true. So a bool of 0 is false, but a bool of 1 is true, as we've seen, but a bool of 1234 is also true. So it's important to remember that anything that isn't either 0 or false will become true. And that's a summary of the type conversions which are available in Python. Iterables and iterators. This section is going to look at functions you can use with iterables and iterators, and the first one is going to be len, which tells you the length of the iterable that you pass it. Here's a list filled with some randomish numbers, and looking at len of A shows us there are 9 elements within that list. And we can see that that list does indeed have 9 elements. Next up, any and all. Any and all work on the Boolean values of the iterables that you pass to them. As we've seen earlier, any entry can be considered to be true or false, but to simplify matters, the 3 lists are going to explicitly use true or false. So in the case of A, all 3 entries are true. In the case of B, some of the entries are true, but it has a false present as well. And the third list will have all false values. So these are the 3 possibilities which are present. If we look at any, we can see that any of A is true because some of them are true. In fact, all of them are true. If we look at any of B, that's also true because it has some true values, even though they're not all true. Looking at any of C gives us the result false because none of them are true. The partner of this is all. If we look at all of A, because they're all true, we get true. As you can see here, all of B gives us false because not all of them are, because we have 1 false value there. And as you can imagine, for all of C, we also get false because there are no true values, let alone all of them being true. For the next section, we're going to define a variable D as a list of numbers. And as you can see, it has 9 elements in it. Let's look at the reversed function. So if we define E as reversed of D, we'd hope to get that list out backwards. And if we look at it, we don't get exactly what we're expecting. What you may have been expecting is a reverse version of that list, and instead we get a reverse iterator object. Now, most of the time in your code, that will be okay, but some of the time you may want to see that list, for instance, when you're debugging or printing out. So if we do list E, you can see that list is D in reverse. But that works how you probably expect, and sometimes you will need to do this. But often within your code, you won't need to do this because Python will deal with the iterator. Instead of casting all of this to a list in one go and outputting it, Python will do it in a more efficient manner and only produce the value which is needed when they're needed. The analogy I can think of is imagine having a machine which could produce cars for you. You'd have 2 modes it could operate in. One where it produces all the cars you need in one go, and one where it does them on demand. That would be fine if you only needed 1, but if you needed 3 million of them, you'd need to find somewhere to store them all. In this case, it's storing all those numbers in memory, and it takes time to create them. Generally, Python's create-on-demand system is a more efficient way for it to work and is much lower on memory demands, but sometimes dealing with this when you're starting out means you need to cast things into a list to understand what's happening behind the scenes. With that out of the way, let's look at sorted. Now here we're defining F as the sorted version of D, and if we look at F, it works the way we'd expect. It produces a list, and it's the elements of D here which have been sorted. You can see we've got 2 7s, which is why we've got 2 7s there, but this list is exactly as we'd expect. And it's also possible to reverse sorted if you need it to be that way round. Next up, let's look at range. Now range is really useful, you may have already encountered it. And if we enter range here in the REPL, we get this range from 0 to 10, which isn't that helpful because it doesn't really tell us what's going on. But if we cast that into a list, we can see we get the values 0 to 9. Remember, it's not including this final number, so it's 0 to 9. We get 10 in total. Now, it's possible to pass it explicitly the start and end values and also a third value stride. So here we can see its range of 0, 10 with a stride of 2. That gives just the even numbers, 0 to 8, and again, it doesn't include the last number. Range is extremely useful and you've probably used it already, but you may not have heard of these last two. Zip and enumerate, which are easier to understand in the context of a program, so I'm going to switch over to code now. Iterables and iterators enumerate. So as a demonstration of this, a simple program is going to be created, which is going to print out the list of players of an imaginary team. So a typical thing, we have a list here, and we're going to create a for loop for player in players, print player. Fairly piecemeal stuff, and you've probably seen something like this before. So if we see that in action, it works exactly as we'd expect, printing each name on its own line. But quite often, it's important to know which number on the list is which index in the list. Now, the way you would probably do this, if you weren't aware of enumerate, is to create a count variable, which is initialized before the loop starts. We'll print the count as well as the player out on each line, and then after that, the count gets incremented with count plus equals 1, and that'll work just fine, as we can see here. But Python provides us with enumerate, which makes a much cleaner way to do this same functionality. So we're going to delete the count variable, we're going to delete the increment of count, and then we're going to wrap players in the enumerate function, which outputs two things. It outputs the normal player, but it will also output the count, a zero-indexed counter of the number of times the loop has run. So we have much neater code. You don't have to worry about initializing or incrementing the count variable, which everyone has forgotten at some point, and running the code gives us exactly the same output as before, but it's a much neater piece of code to read. It's easy to see exactly what's happening, and because it's standard code, you'll get used to seeing this and understand it intuitively every time. Iterables and iterators, zip. In this example, you have two lists which need to be paired together. So in this case, a list of 3 countries, and one of which is continents which go with them. And you want to create tuples with these paired together. Now, the way you would initially do this would probably involve a for loop. So in this case, using an index variable, combining range and the length of the countries list. So that index will now allow us to access the countries, I, and continents, I. We can check if that works by running the program. And as you can see, they've been paired correctly, France with Europe, Tanzania with Africa, Canada with North America. Now that we know we're accessing those correctly, we can put these together. So first things first, let's create a list for them to go in. So here's our empty merge list. And then we can do merge.append and put that in brackets inside there. So we create a tuple with those two together. Finally, we can print out the merge list. And there we can see that running, and we have our list with the appropriately paired countries and continents. Now, if you're not aware of the zip function, this is probably the kind of thing you will do many times. But there's a much simpler way to do this. And as we can see, we can use merge2. It uses the zip function with those two lists, countries and continents, and that's that entire for loop replaced. When we run this, they both produce identical output, but this is a much more complicated equivalent to this. So the zip part is much simpler than this 3 lines where you create an empty list and a for loop. It could have been done with a list comprehension, but still would have been complicated. But zip works faster, is much easier, and it's much less error prone than the manual approach. It's important to remember that this is a zip in terms of a zipper on your clothes, not in terms of a compressed file creator. But zip is incredibly useful whenever you have lists you need to merge together. Iterables and iterators, iter and next. The last thing we're going to look at in this section is the creation of an iterator, such as we saw earlier on. It's possible to create an iterator using any iterable, and we're going to use a list in this example, and then it has a method next, which pops the next value off of that iterator until it's exhausted, when you'll get a stop iterator exception. So let's make an example now. So here, a equals iter, and we're just going to pass it a list directly of 1, 2, 3, 4, 5, and 6 to keep it nice and simple. So now we've created our iterator A, and now we can just use next A, and we get the next value from it, and then 2, 3, 4, 5. And once it's exhausted, if we try next again, we get a stop iteration exception. This is the way that any iterable works behind the scenes with Python. So anything which can take an iterator will work exactly the same way with an iterator you've created using the iter keyword. Input and output. So in this section, you're going to be taking a look at features which are classified under input and output, and particularly in this case, it will be print and open. Print is probably the first thing you came across ever, which you can see here with print, the archetypal hello world, and obviously that returns hello world. But there are other values which we can use with print, as you can see here in BPython, and one of them in particular can be really useful, which is end. So you can see end there, and it defaults to the new line character. Now this is going to be shown to you in the context of a program to see how useful it can be when printing out multiple values to the command line and you don't want them on separate lines. So flicking over to code, you're going to see a program which is a toy example, but will show you how useful this can be. So all this program is going to do is print out the numbers from 0 to 99. So we have the range constructor here, which is just going to print those out. And seeing that in action, you can see it running. And we get those numbers. We can see we've got 100 lines printed out, and it can be difficult to see everything which is happening on screen at once. Now, if you don't want that, you can make use of the end variable. So we can set this as default. End is the new line character we saw earlier on in the course. So instead of that, let's change it just to be a space. And now when it's run, you can see that all of the numbers are available on screen at the same time, even to the point where we don't get a new line at the end of the print, and our prompt is on the same line as that last print. And you can see that can be fixed with just a blank print statement, and running it again, you can clearly see where the program stops. And this can be really useful for dealing with programs where you have a lot of printout which comes onto the screen at the same time, and you may end up scrolling from hundreds of lines. This can make it much easier to deal with. Next up, open. Here, open is going to be used in a fairly simplistic way, and this is not what you'd do typically, because normally you would use a thing called a context manager, as you will see later on. But here the example will make sure the file is closed by explicitly closing the file object. Here we'll start with the file object being defined using the open function. And here it takes two values, the name of the file and the mode in which it will be opened. In this case, write. So here we have test.txt, and that's going to be opened in the write mode. Once this has been executed, we have a file object that we can now access. And one of the methods that it supports is write, and we're going to write just some text as seen there. So we're going to write hello world, and you'll see there's a new line entered at the end with \n. And finally, you should close the file object, in this case, with the close method. As mentioned previously, typically you would use a context manager, but this is going to ensure the file is manually closed in this simple example. So here you can see the program running. There's no direct output, but looking at a list of the directory, you can see test.txt exists. And if I use more to examine the contents of test.txt, you can see the text hello world has been created. Now clearly this simple example could be expanded by adding more text, but you can see the basics of how open works to open a file on the computer's hard drive. The other way you're going to see here is in read mode. So to make the code difference clear, I'm going to comment out the original writing part of the program and see how it's opened in read mode. You can see that the open line is very similar with open test.txt and read. And this time, the file object gives us the read lines method, which reads all the lines of the file as a list, and then will ensure the file is closed. So this time, once it's run, you can see that we have a list of the text which is present, including the new line character. And that's the very basics of reading using open. If you want to look further into this, RealPython has a course on reading and writing files, which will show you much more about how open works, the different modes available to it, using context managers, and how to deal with the contents of different types of files. Variables, references, and scope. Variables, references, and scope. Duh. One of the most useful functions that I found during my time using Python is dir or directory. This allows you to see all of the attributes and methods that any Python object has. This may seem a rather abstract concept, but it allows you to understand what you can do with any object. Let's create an object and get started with it. So firstly, we'll create a string. So here, the string A is hello. And we may not know all of the methods that you can apply to it. So for instance, you might know a.upper provides an uppercase version of that string, or you can use a.capitalize to capitalize the initial letter of the string. You may have forgotten what methods are available to you, and if you're not using something like bpython, they may not be pointed out to you. Now, while this may not give you the full documentation on the methods or attributes that are available, it can jog your memory or allow you to search for the right term. So here, using dir on A, we can see we get all of these methods and attributes which are available for a string. So some of these may be immediately apparent, some of them won't, but they're all things that you can examine in more detail or do a targeted search or experiment with them and see what happens. It's a really important part of learning to understand things in your own terms. Often other people's explanations may not really hit the mark, and if you've experimented with it and understand it in the way that you need to, then you'll know what to do with an object and be able to use it most efficiently. So here we've discovered the method a.center, and if we put in 50, we can see that it's centered the hello string within a 50-character gap, which can be really useful when trying to produce headings, etc. And it's exactly the kind of thing that I replicated myself in code, which worked out how long the text was and how long the spaces were, and it took me many lines to do what center could do in a single method. This works for any kind of object in Python. So this is hugely useful and really important. So no matter what kind of object you're dealing with, you can perform dir on it and see what kind of methods and attributes it has. So here we're importing datetime and doing dir on datetime, and we can see that inside it, there are other submodules. Now, I happen to know that datetime.datetime has some useful things in there, so we can do dir on datetime.datetime, and in there, there's a list of functions and attributes which we can experiment with or search for to know exactly what we're dealing with. Now, the slightly intimidating part of this is all of these, what are often called dunder methods with a double underscore, and these are generally part of the internal working or initialization of objects, and they're things that you probably won't need to worry about at this stage, but as your programming develops, you may need to make use of them later on, and you'll know that they're there. But for the time being able to find out what kind of things an object support, or even if an object is what you think it is, can be really useful, and then you can look into experimenting with them to improve your understanding of what's going on and what you can do with an object. Variables, references, and scope, vars, and globals. Scope is something which is initially difficult to understand when starting programming, and globals, locals, and vars allow you to understand scope a little better. This is best demonstrated in the context of a program, so here you can see a program with A being equal to 1, B being equal to the string global, and C being equal to the string another global. As you may know, within a function, the same variable names can be redefined with different values, and they won't refer to the same actual variable. So here, defining a function where A is being set to 2, B is being set to the string local, and then those two values will be printed out. Meanwhile, in our main scope, we will print out the values of A and B, then call the function, which will print those values out, having defined local values of them, and then we're going to print A and B again to see whether or not they've been permanently altered while in function. Let's see that program running. And you can see that here we're in the global scope. So that's this line here, line 10. And there we have the local versions of A and B being printed out. And then once we're back in the global scope, A and B are back with the values we would expect there. Now, sometimes it's difficult to know what variables have been defined or available to you in any given scope. This example is a fairly simple program, but understanding what's going on in a more complicated program can be more difficult. So one function which is particularly useful is vars. So here, if we print out vars, it will show what variables are available in this scope, and it will print them out in the form of a dictionary. So running the program, you can see that where we've printed out vars, the available variables in this local scope are A is equal to 2 and B is equal to local, which is what was printed out. However, if we take that code from line 9, so exactly the same thing, print vars. If we put that at line 14, after we're back in the global scope, you'll see that there are more values available. So here we have this much bigger dictionary of values, but the most important things for us at this point is that A is equal to 1, B is equal to global, and C has a value of another global. So different values are available depending on what scope we're in. As you've seen, these are the vars which are available in the global scope, and instead of printing vars, you can print using the function globals, which gives us the global scope variables at any point. So here you can see it gives the same output because the vars are the global vars when printed out in the global scope. However, I think this might muddy the water slightly because it's a different function. It doesn't illustrate the difference in the variables available in the function and the global scope are the same, because you could print globals out while inside the function. So if that gets printed out while inside the function, so if we move globals to be printed inside the function, you can see that these are the local variables and these are the global variables. So if this is printed out, you can see at exactly the same time, the global value of A is 1 and B is global, whereas A is 2 and B is local. So that can get a little bit confusing, but it's certainly really useful to be able to print out vars because you can understand what variables are available to you at that point in that scope. And if you're unsure what scope a function is running in, you can use vars to understand what's going on. But there is something else which also muddies the water slightly, which is if we print out C, it's not defined within this function. So if we can't find it in the local scope, it will then see the value of it from the global scope. So if we run that, you can see that despite the fact that it's not defined in the local scope, C is accessible from the global scope from line 3 because it's not defined within that function. Now this is something you need to spend a bit of time getting your head around, but once you understand it, it will help with your understanding of what's going on generally, but it's easy to tie yourself up in knots, particularly if you use the same variable names inside a function as outside a function. So the local A is different from the global A, which is why it can get confusing, and it's a good idea not to name your local variables with the same name as a global variable. And many IDEs, such as PyCharm, will warn you about this, and that you're redefining a global variable with a local value. By avoiding this local reuse of global variable names, you'll remove one step that you need to make in understanding what's going on in your program. Miscellaneous. Miscellaneous, exec. Exec is a function which allows you to execute any Python code. Now, you may have seen warnings about using this. Initially, it looks like a really great idea because you can execute any Python code that you input into it, which allows you to construct the code from the program and then execute it. But you have to be extremely careful about this because it can execute any code. And this toy example will show you why this can be dangerous. In this case, elsewhere in my program, I happen to have imported the OS module, which gives you lots of useful features to do with the operating system of the computer the program is running on. And it gives us access to lots of really useful functions. And it's quite common to import OS as it allows you to construct file paths, etc. So let's say that's happened. And now the rest of our program allows us to input some code, which will then be executed. So we'll have job equals input, tell me a task to do. And now I'm going to be able to input any Python I want, and then we're going to execute that using exec. That looks great. So now instead of me having to write some Python code, I can just enter it and that will run it for me. So let's see that working. So here we see it running in the manner I intended. So it asks for a task for me to do. And as you can see, I can enter print hello world. And it will execute that. And that works. And that's great. But the problem is we've now allowed the execution of any Python code. And unfortunately, in this case, because I've imported the OS module, I can execute a program on the system that it's running on using os.system, in this case, just ls, which lists the directory in which the program is running in, and we can see all the files that are there. So now running it again, I can use another OS system call and remove one of the files which is present, in this case, test.txt. And that has deleted that file. And just to run it again, pass it os.system ls to see a listing. And you can see that test.txt, which was previously present, is no longer there. It's now gone. And this is why you have to be extremely careful when you use exec, because it's possible to do something which can damage the system. So you have to be very, very careful to ensure that what's going into exec has been completely sanitized, because if not, you could open up yourself to things such as deleting the entire system. So with one command, it would be possible to delete many of the files off the Mac that this is running on. I'm not going to give that as a demonstration. So while exec is powerful, it's best avoided unless you're sure you're being really careful with it. Miscellaneous, eval. Similarly to exec, eval allows you to evaluate the value of a Python function. So it's often the kind of thing you'd use for a calculator, etc. So in this case, another toy example is going to show this in action. So calc is equal to the input, give me some maths to do, and then we're going to print the value of eval of calc. So it will work out calc and then print that out. So let's see that working. And here we can see eval.py runs. And if we give it some simple maths, 5 plus 7, it works. But as we've seen with exec, there is a danger. If elsewhere in our code we've imported a library such as OS, that will be accessible. So we can do much the same as we saw before. So if I enter os.system ls, we'll get a result. And you can also see we have the result 0 because it didn't return a mathematical value, but it did return the listing. And again, we can attack our system using other system commands. So here I can delete me.txt by using os.system rm and then the name of the file. Lo and behold, that's gone. If we list that, you can see that delete me no longer exists. It's been deleted and it's gone forever. There is a way to limit this with eval. So after the argument which will be evaluated, you can pass a dictionary. So here, an empty dictionary will mean that no named functions will be accessible. So now our previous attack using OS will not be accessible because it's not in that list of functions. So if I try it this time, you can see that we get a name error because OS is not defined. To add a function that you would like to access, you can add a dictionary in this format. So here's the name it will be accessible by, and then you can add the function in. Remember, no brackets on the end as we want to add the function itself. And now we can use pow. So in this case, we can enter pow 3 and 2. And as you can see, that returns the value we would expect. So eval can be made safer using this technique, but it's important to ensure with anything which will execute code that you are not executing unwanted code at any point. This is clearly not going to be a problem if you're the only user of the code, but many has been a time when such code has then been allowed to be used by others and problems have arisen. So be really careful with both exec and eval. Miscellaneous, hash. The hash function is extremely useful. It may be something that you've heard of when downloading files, etc. for checksums, but simply put, a hash is a one-way function which gives a summary of the contents that it's been passed. So in this context, it could be a string, an int, or any other variable or object that's been passed. In Python, it's easily accessible using the hash function. And here you can see that printing the hash of 123 leads to the value 123. So the hash of any int will actually be the value of the int. So any integer, as you can see here with 123456, is the value of the number itself. As soon as you work with text, as seen here, the hash is a lot bigger. But now you're going to see how this can be useful. If you have two pieces of text which are very similar, so here the text hello from real Python with an exclamation mark, and here the same text with a full stop at the end, so one ends in an exclamation mark, one in a full stop, and that's the only difference between the two. Running this shows that these two hashes are completely different despite this small difference between the two inputs. As a result, it's very quick and easy to see if there's a difference between two supposedly identical files or inputs. So in that previous example, it was easy to see the difference between the two visually, but here you're going to see it applied to the entire content of a book with a single character's difference between the two. This is going to make use of the file open command, which you saw earlier on in the course, but it will be placed inside a context manager. Again, if you're not sure how to do this, have a look at Real Python's course on reading and writing files. So here we're going to use the with context manager, open the mobydick.txt text in read mode using R, and then that's going to be referred to as file obj in this context. And then the moby list, which will be a list of each of the lines in that text file, is created using the file obj.readlines method, which reads all of the lines from the file object and places them into Moby list. So that's the first step, and the file has now been closed. And now we're going to create two texts. So the first one, Moby1, is using the join method with Moby list. So that will turn Moby list into a single string, and Moby2 is going to be exactly the same. At this point, these two are exactly the same, and we can check that by checking the equivalences of the hashes. So here the print statement contains the equivalents of hash1 and hash2, and if they're the same, we should see the output true. So let's see that in action. And we see true because they're identical. Next, Moby2 will have a single space added to the end. This is simple to do using Moby2 plus equals space. And now we'll repeat that checking of the hash equivalence between the two and run that. And we can see they're true before, but afterwards the hashes are different. Now let's print the length of Moby1. And you can see that this is over 1.2 million characters, which it's checked that quickly and told us that they're not the same. Now clearly doing that by hand would be incredibly long. Even writing a for loop that checked through each character would be a very long-winded way, whereas using hash allows you to check quickly and accurately whether two objects are identical. Not the same object, but whether their contents are identical. Well done! You've reached the end of this course on basic data types. You've seen what ints are and different ways to construct and convert them to different formats. You've looked at floats and seen the different ways of creating and converting those. You've looked at complex numbers. You've looked at strings, different kinds of strings such as raw strings and triple quoted strings, escape sequences, and the methods that you can apply to all of those kinds of strings. You've looked at Booleans, true and false values, and the truthy nature of Python objects and comparisons. And you've seen a wide range of built-in functions which allow you to speed your Python programming, making it more efficient, more reliable, and faster.